I have to say that I'm sharing, have to change. Now there is a international symposium on landslides from Cartagena, also online. I'm trying to move between.
Oh. So Ray, may I put my introductory slides up first, just to give you an introduction, and then I will.
Of course, I have to stop sharing.
Yeah, I think so.
There you go.
Great, and then I'll get this this one up. I think for questions, if we ask people to put things into the chat, or you can field questions as you go, Ray. But I guess what we do is we collect things in the chat and then we go through them. Christoph, as overall host, do you want to be in charge of the questions?
Yeah, I'd like to. Yeah, why not?
Somebody needs to mute.
Yeah, Kannadbek, is your microphone still on?
No, it's not my.
Okay, so Richard, we can see your PowerPoint, but not in presentation mode yet.
Passcode you sent me doesn't work.
Yeah, it does.
Yeah.
I just typed it in.
8941.
No, there's not 89. This isn't the.
Oh, well, the one you sent me. Okay. Do you know the number?
We have to click on the right meeting. You're in the test thing we did, not in the actual session.
I just clicked on.
Okay, it's 8208. I think it's there. 5.
Okay, well, I don't know the password.
Look at it. The email.
I did. It's right here. It's 89.
Here, 820815.
Oh, I see. Okay, that's mine. Okay.
Wonderful.
I can't hear anything.
Can you hear me now?
Yes, now I can.
Okay, so Richard, you're muted. You wanna start?
Okay, so yeah, if we're ready to start then, so look, welcome to all of you. I just looking through the windows at the people who are presented here. I think we kind of cover most time zones, most continents. So thank you very much to those of you in Eastern Asia who've stayed up late in order to listen to us. Thank you to those of you in the Western United States and South America who've stayed up or woken up early to listen to us, and welcome. And thanks to this, which is the first in what we hope will be a series of lectures running once every 2 months, which we are folding into part of a project which has really come from a project that started this year, which is this project, looking at earthquake hazard and environmental security in Kazakhstan and Kyrgyzstan. This is a project that's supported by the NATO Science for Peace and Security program, and it's one that has brought together a number of international researchers, right? So here we go, the 3-year international project supported through the NATO Science for Peace and Security program. I'm involved, Richard Walker, for those of you who don't know me, University of Oxford, United Kingdom. Kannadbek Abdrakhmatov from the Institute of Seismology, National Academy of Sciences in Kyrgyzstan, Natalia Mikalova from the National Nuclear Center in Kazakhstan, Ramon Arrowsmith from the USA, Magli Riza from France, and Christoph Grötzner from Germany. Within this project, there's a bunch of things that we're trying to do over the next few years. First of all, it's a chance or an opportunity to investigate distributions of active faults, slip rates, earthquake histories, all of these kind of earthquake geological style studies, with a particular focus on those places which are important for regional environmental security. A second important theme within this project is to try and build capacity through a program of training, in-person training activities, workshops, all of these things, and also equipment procurement in partner institutes, the partners in Kyrgyzstan and Kazakhstan. And thirdly, and also very important, is to try and then work with end users to implement our results into hazard assessment and into risk reduction activities. And that's kind of our long-term aspirational aim. I should say, of course, that this program started in the summertime, and a lot of our activities are postponed. We haven't been able to do these in-person training activities. We haven't been able to perform any of the field works that we would wish to do, and so we've also let's say taking advantage from some of these delays by looking for other things that we can do. And what we've tried to do with this lecture series is to give some showcase or to showcase some of the world-class examples of active faulting that you see within the Tian Shan region, within Central Asia, to show that to a global audience, to share ideas, and to bring some focus to the earthquake hazards and the earthquake geology of these regions. Just to give you one, on the background here, this is actually an earthquake rupture from the Chile earthquake. This is a magnitude 8+ earthquake that had a lot of effects in Almaty, regions of southeastern Kazakhstan. And this was an earthquake that occurred in 1889. And you can still see the scale of this, 10 meters of displacement, still very fresh in the landscape. And so there's a lot of things that we can learn from looking at these areas. They really are spectacularly exposed and preserved. As I say, these lectures, we're hoping to run them every 2 months. There is a plan in terms of the timing. We always do our activities for this program on the last Monday of the month. And so we're going to try and run these lectures, these public lectures, once every 2 months. And so it's going to be the last Monday of the month. It's going to be Monday, 26th of April, 3 p.m. GMT, right? We choose the UK time so that we can try and maximize the number of time zones that we can have people from, right? Early morning to late evening. In terms of advertisements for this, we will promote these through we have a Twitter feed, Earthquakes in Central Asia, Quakes Central Asia here. Also the website that goes along with that, quakesincentralasia.org. And so these are really where you're going to get information fed through from us. And so that's really, I just wanted to give you a bit of a background as to why we're doing this, and to show that it's part of this this wider long-running program that we are attempting over the coming years. Who we're going to hear from today is actually a great pleasure to be able to welcome Ray Weldon, who has volunteered to give this first lecture, which I think is going to be somewhat of an overview of the long-running research collaborations he's had with Kanatbek in the geology of Kyrgyzstan, but also some emphasis on some of the programs that he's running right now, with a focus on looking at earthquake hazard within Bishkek. I'm sure you all, or many of you, kind of know Ray or know of his research already. Just a very brief biography. Did his studies in Pomona College, PhD in Caltech, then a short period of time at the USGS Hazards division, and then moved to University of Oregon, where he's been for the rest of his career. Obviously very wide research outputs and experience from many different countries, working in the broad field of earthquake geology and active tectonics, but also many service and advisory roles, and also lots of outreach activities and capacity building activities. And I think a lot of that are going to be themes that we're going to see in Ray's lecture. Just a reminder to all of you, please try and put mute your microphones so that we don't have any background noise. Please, if you have any questions, just put them into the chat. And what we're going to try and do is we're going to try and feed through those at the end. thank you very much. And I shall stop sharing and hand over to Ray. Thank you. And welcome, Ray.
Well, first of all, thank you very much, Richard, for that really expansive and generous introduction. It's really my pleasure to have this opportunity to talk to all of you. I don't know if you can see my outline. The pictures are in front of it.
I think you need to reshare. We're seeing your email at the moment.
Oh. Are you seeing that?
Yes.
And full screen?
Yes.
Okay. And can you see, I can't see on the side the words that tell who supported it.
We can see that.
Okay, good. Okay. So first of all, I want to acknowledge Unison, and I think I saw Cassini on the picture there briefly, and also the National Science Foundation and others that have funded this project. As Richard said, I've worked there for more than, I think I've been there 14 summers over the past 26 years or so. I've spent a lot of time there. It's been wonderful to do so. And in particular, the program that allowed me to take a field camp over there for 6 years was very critical to what we're doing. I'll talk about that a little bit later, where we were training both EU, Central Asian, and American students together. And my current project is also a training project, and I will motivate that in a few minutes. So first and foremost, I need to thank Kanat Beck there, looking a little grim in the morning as he takes his coffee. And it's been a real pleasure to work with him. And of course, none of this would have been possible without him. I also want to acknowledge the, hey Kanat, I also want to acknowledge the geology of Kyrgyzstan. It really is the most remarkable place I've ever worked. And in particular, if we look at the bottom right, the bedrock is well exposed. It's well mapped from a lot of effort during the Soviet era. Above the bedrock is a remarkable erosion surface on the upper right that sort of divides the old geology from the new, with the Neogene sediments on top of it there. I'll talk about that a little bit as well. And then, of course, we have an incredible record of Pleistocene deposits and terraces and other things like that. Bottom left is Mike Bullen there. And so really, it has it all. And so it's really quite remarkable. And it's really a place where we can combine these elements. And that's going to be something I'm going to try to focus on today. Those of you who don't know where it is, and this will be quick, it's shown here on this seismic hazard map. This is an old slide, but the point I want to make is by most measures, Kyrgyzstan has the highest seismic hazard in the world. And that obviously also motivates us to work here to see what we can do to characterize and hopefully mitigate the hazard. Zooming in a bit, and still introductory material here. It's driven, as I think all of you know here, by the collision of India into Eurasia. And as you'll see in a moment, more than half of the deformation is in the boundary zone there. More than is actually occurring in the front of the Tibetan Plateau, or at least it's about 50-50. And so it's really quite remarkable in the sense that we have such high rates of deformation quite a ways from a plate boundary in the interior of a continent. Love this picture that Kanat Beck gave me. This is just 2 years of earthquakes from his network. And so you can see, if you weren't already aware of the fact that there are lots of earthquakes here. And obviously there's a considerable seismic hazard that we have to worry about. As Richard mentioned briefly, and I just threw these up as well, there are also extremely large historic earthquakes, and they have actually been very well studied and continue to be studied, as Richard mentioned. The bottom left was a report done by the Russians that was very much like our Larsen report after the San Francisco earthquake, and really very, very important in understanding earthquake geology. And again, just some slides up here to motivate the fact that there are historic large earthquakes, there are little earthquakes everywhere, and obviously there are active faults and considerable seismic hazard. So, as Richard said, I'm going to try to give an overview of some of the things that we've done and places we've worked, and also focus a little bit on our current project, which is to better characterize the seismic hazard in Bishkek. So I'm going to run through some slides. I apologize to those of you doing more recent work, because really the bulk of our work was in a continental dynamics project in the 1990s, and then in the 2000s, the field school that we ran. And I haven't made an effort, I'm sorry, to incorporate newer things that people have done. So don't think I'm ignoring you. I'm just trying to give an overview of what we've done here. Principal goal of this, at least the part I was involved in, was to make a transect through the Tian Shan to recognize and get slip rates on the faults, which is shown in that central figure there, and then to compare it to the GPS network that was installed as part of that. And you can see in this paper, led by Steve Thompson, one of my students who did a remarkable job on this project, shows that the GPS and the slip rates on the active faults are very consistent, and more recent analyses of the GPS and updates on the slip rates confirm this. We mapped lots of cool faults. We trenched and got slip rates, and in a few places recurrence intervals. Again, I think most people on this talk are familiar with the work and are familiar with these techniques. So I'm going to focus a little bit more on the things that we haven't been doing that I think we should be doing more of, and also on the seismic hazard implications. The bottom right is a figure that Kanat gave me to show, this is a summary he's made to show all the places we have slip rates on faults, and you can see there's quite a lot of them now. So I think we know from the GPS and the seismology and from the slip rate studies, at least in this sort of transect area of the Tian Shan, where the active faults are at the surface, what their slip rates are. And we're learning more and more every day as people do more trench studies, the timing of earthquakes, which wasn't a focus of our project. But as you can see from the figure on the left, we did actually date some earthquakes as well. Over the last 4 or 5 years, Kanat Beck has asked me periodically, which of the seismic hazard maps should we believe? Because there's been a proliferation of seismic hazard maps for Kyrgyzstan, also for Bishkek. I'll show some in a moment as well. And they're all somewhat different. So I did what I usually do, is I called up Steve Thompson, who is sort of my go-to guy on this, and said, okay, Steve, which one? And he said, there's probably no difference between them if you consider the uncertainties. So basically they're all the same, so pick what you want. Of course, Steve is always right, and he is right. However, the point is, the way they differ tells us something about what they either have or don't have going into them. And I think these differences are important, as I'll try to argue in the next few moments. And so our current project is effectively to review the existing hazard estimates for Bishkek, take from them what is good and try to identify what we don't want to use, and then put the pieces back together into the best possible seismic hazard estimate that we can make from the existing pieces. And this will be done in the context of a training course, which will involve both Kyrgyz and Americans, funded by Unison, so that they're learning how to do this as we do it. Just to motivate this, I was called by the US Embassy soon after I gave my short answer to Kanabek of what Steve told me, and they were interested in the very same question. And I said, okay, fine, buy me a plane ticket to Bishkek, and I will research this a little bit and tell you which one to believe. As you can see, I'm not very bashful when it comes to getting some money to go to Kyrgyzstan. Anyway, I think it's interesting because the embassy was building a new building. They had geomatrics consultants through the State Department do a study of the site. They came up with the numbers that you see here, peak ground acceleration, and a probability of exceedance of both 10% in 50 years and 2% in 50 years. This is personal communication from John Egan, a colleague of mine. I later learned that the report was confidential and he wasn't supposed to tell me about it. Oh, well. But anyway, the 2005 paper by Erdick et al., which was done with the USGS Earthquake Hazards Group, had very similar numbers. And they talked about 2% exceedance in 50 years. And they had a gradient across Bishkek from essentially about 0.6 G to about 1 G from north to south. And they had about 0.9, just as the geomatrics report did for the site of the embassy. And so what the embassy did is they started telling their employees to look for housing on the northern part of Bishkek because it'll be much safer when there's an earthquake. I'm sorry, on the southern part of Bishkek, because it'll be much safer if there's an earthquake, because they get 0.6 at the north and 1 at the south. But then the Potsdam group, they did a study that started coming out in 2015, again with Kanabek, focusing on site response, and I'll show some pictures in a moment. But they got similar average results, but basically had the opposite gradation. In other words, they had the greatest hazard on the north. Without going into any of the details, these are some figures from the Potsdam group, and these are different spectral frequencies, but they all tell the same story. You can see the hot colors are on the northern part of town, and essentially the colder colors are on the southern part of town. And this was exactly the opposite of what the studies that the embassy had done early were telling us. If we look at the geology, we can see why. So on the left is a geologic map of the Bishkek area, and on the right, I've zoomed in a little bit. And again, I show this also in part to make the point again, there really, really are excellent geologic maps. We really know quite a lot about the superficial geology and the bedrock geology in this country. If we look at the zoomed in one on the right, the texture with the little triangles on it are alluvial fans. And for those of you who've been there, it should be no surprise that most of the southern part of Bishkek is alluvial fans coming out of the Kyrgyz range. And as you go farther north, you get increasingly fluvial deposits, as you can see on the map. And eventually, when you get near the top of the sort of greater Bishkek area, you're down by the river there, and you not only have really fine deposits, but you have some marshy areas and things like that. And so it shouldn't have been any surprise that we would find that the site response would produce greater shaking to the north than to the south. The problem with this is their source model. Their problem, in my opinion, is their source model. So they used what's called an area source. An area source is where you make a catalog, usually from historic and instrumental data. You then break up the region into sort of seismotectonic domains. You can see the different polygons on their maps, how frequent earthquakes are in the different model. When you make your model, you randomly drop earthquakes into the polygon. Now, what's lost there is the fact that we have a picture is looking actually out of Convec's apartment, which I've had the pleasure to stay at. I just would be too surprised to learn that there's a thrust fault between us and the mountains there. And of course, some people on here have worked on this problem. The Issaquah fault, and it will be studied, a small map that's shown sort of in the left side there, and recognize that there's a fault bend fold as the fault approaches the surface. And by looking at the uplift and the height of the back limb. Without going into the details, though, I'm going to come back to this kind of analysis in a moment, essentially just using the geometry of that boundary and the uplift of the terrace. You can get the slip rate. Is the thrust fault, and you would expect to see greater shaking to the south and lesser to the north if we ignore the site response. So the point is, what we see here is really an excellent job on the site response, but I think we can do a better job on the source model. To return to this distinction that was worrying the embassy here, the earlier studies used what are called line sources. They knew that the thrust fault was there. They used the slip rate that we had developed on the Issaquah fault. And essentially what a line source does is takes the surface outcrop of a fault and then reduces the shaking with distance from every point on that line. And this is something that's commonly done and works quite well, especially for vertical faults like strike slip faults like the San Andreas and things like that. But as I'll show you in a moment, doesn't work quite so well for dipping faults. And this is one of the major things that I want to emphasize in the rest of my talk. My point is that each of these have something of use in them. In particular, the Potsdam group has done an amazing job on site response here, and other people have done a good job on the on basically the bedrock shaking angle, but we need to put the pieces together right. Now, the line source doesn't work very well either. And again, this is from an old paper. You can see the date down there, 20 years ago, almost to today, where we made a cross section through the range approximately where the Chu River cuts through. So this is at the very east end of the Kyrgyz range where the exposure is quite good. And again, we were focused on this erosion surface. So if you look at the bottom figure, we could map the erosion surface up the backside of the Kyrgyz range, and the surface extends down under the Kashgar Basin. We could see it on top of the range. We could see it in the front. In fact, the continuation of the Issaquah fault becomes blind there, and there's a back thrust. And essentially, this end of the Kyrgyz range, at least, we believe is a giant fault propagation fold that is broken through. And if you look at the scale here, when you get to seismogenic depths, let's say 10 to 20 kilometers deep here, actually the fault that will cause the earthquake is almost 40 kilometers away from the populated areas in the Chu Basin. And in fact, I will boldly predict that when this thing goes, the shaking will be worse in Kashgorka than it will be in Bishkek. And you can hold me to that when it happens. Okay, so the point I'm trying to make here is that we need to know more than just where the surface expression of this fault is and put a line along it and reduce shaking as we go away from the surface. Near Bishkek, there aren't very good cross sections. Sorry if Mike or Doug are listening to me. But if we look at the map first, what you see is that there's an anastomosing set of faults and folds. And in fact, if you look to the right edge, the Issaquah fault becomes blind, as I noted. And clearly, all of these structures we see are just a surface expression of something deeper. The bottom left figure is something that Kanat Beck tells me that Steve Thompson and I made light years ago, but I don't even remember it. So maybe Steve made it, but it still makes the point. If you look at the numbers in that horizontal line in there, which are hard to see, they start at 0, which is downtown Bishkek, and go all the way to 30. And even 30 kilometers away from downtown Bishkek, the fault we think is still only like 3,000 or 4,000 feet deep. It doesn't reach seismogenic depths until you're a considerable distance away. The section on the right by Bullen and Burdock and Burbank is similar. Now, why does this matter? Well, we know from thrust fault earthquakes around the world, and this is probably the best one in Taiwan here, that this really affects the shaking. So if you look at the left there, the Chilangpu fault ruptured. We know that it had surface displacement. The epicenter was behind it. And if you look at the little cartoon cross section there, you can see where the hypocenter was. And it was considerable distance from where the surface rupture is, if you look at the scale. In fact, underneath another fault to the south, about the distance to the Kashgor fault. If we look at the map on the right there, the red line is the surface rupture. And what I've colored in is a 0.3. Don't worry about the units, except that the bigger numbers are greater shaking. And with the exception of some hot spots that are in basins, and I'll try to talk about basins later too, you can see that the bullseye of the 0.2 and also the 0.5 is well to the right of the fault, which dips that way. And that's why I made that very confident prediction that when the fault under the Kyrgyz range ruptures, the shaking is going to be worse on the backside than the front side. Okay, I may be wrong, but I don't think I am. Okay, this is something that people do worry quite a bit about. And Richard mentioned that I serve on the steering committee for the National Seismic Hazard Map in the US. And the steering committee is headed by John Anderson, who is the person that I've learned most of this from. And he's been quite focused on the impact of fault dip on normal faults. This is probably no surprise. He lives in Reno, which is the capital of Nevada, and the Mount Rose fault is the principal hazardous fault in the area. So what we do, and what we'll do in our training course, is we'll build a logic tree, such as shown in the upper left here, for the different factors that go into controlling the seismic hazard. Then we'll run a whole bunch of hazard curves, such as are shown on the bottom left. And then we'll make something called a tornado plot, which is on the bottom right. The tornado plot tells us what factors control the uncertainty. And so if you look at it there, Mmax matters a little bit. In other words, how big the earthquake can be. The slip rate matters some. The ground motion equations matter a lot, something we find in all of our studies, and there are ways that we could perhaps improve that in Kyrgyzstan, given all of the small earthquakes recorded by the network. But the biggest source of uncertainty and what the shaking will be at, I think this is Summit Mall, yes, in Reno, is the dip of the fault. And that shouldn't be too big of a surprise, because if you think about it with normal faults, generally people are living on the basin side or the hanging wall side, and essentially the flatter and flatter the fault, the closer and more underneath the town it's going to be. It's just the opposite of in a reverse fault, however. Okay. That gives you sort of an introduction to what we're trying to do and how we're going to do it. What I'd like to do is then give you a whirlwind tour of places we've worked and things we've done. And this issue keeps coming up. The second place I want to talk about is the southeastern part of Issaquah. This is to highlight Reed Burgett's work, who has still been working in Kyrgyzstan. I'll show you briefly some of his more recent work. He's basically worked in the, I want to focus on the southeastern edge of Issaquah, which arguably is the second most important place we need to understand seismic hazards, given the development and the consequences of an earthquake here. You look at the Jetty of Goose area here, what Reed did, in addition to a lot of mapping and also checking of the existing maps, again, as I've tried to say before, we start off with excellent maps already, although there's still some additional mapping to be done. And then he profiled the terraces in the river of Jetty of Goose that you're seeing on the bottom right. And remarkably, what we expected to see there, that big hinge in the map, the big black line, which is a fold hinge there, we expected that to be a thrust. It isn't, though it is on some maps. It's just a hinge. And that hinge is quite remarkable, as you can see, in terms of how it's tilting progressively older and older terraces. So we try to make a model, cross-sectional model, that explains this. I showed you before on the Issaquah how you can use limb lengthening to look at a ramp at depth. This is at the bottom right, but that produces parallel deformed terraces, which we don't see here. And there's other options. One is that there's a deep fault underneath the Tursky Range that flattens as you come underneath Lake Issaquah. Something like this would progressively tilt older and older terraces, as shown by the neogene sediments and also by the blue and green lines there. Or we could have a tri-shear model, which I think is our current favorite here, which would also shear the material in there, and you would have hinges on each end, and you would basically be making a giant fault propagation fold. If we look at other places along the margin where Reed has also worked, this is to show Aktarek, a place that I got to spend some time with him when he was working there as well. Again, I note the excellent map. We really, really, really need to not just focus in too closely right on the ruptures. We want to understand their context, so we've got to go back to making maps. And then you're seeing the profiles that he's made there. In this area, which is in the middle of the map, bottom middle, that obvious stream that cuts through the ridge, maybe even I can point in through here as well. We see quite a complicated set of what's happening to the terraces. In some places, they're being uplifted parallel, in other places, they're being progressively tilted. So we have tremendous insights into what's happening in this area. Also, I want you to note the dashed black line with the teeth and the fold angle down at the bottom of Lake Issaquah. There's a very sharp boundary there that we don't see to the southeast. So it's possible that the causative fault is daylighting, if that means anything, at the bottom of the lake there. And all the things that we're seeing at the surface is just noise associated with this giant feature. Now, again, the point I want to make is that we might try to say, well, okay, we've got all these active faults and we're going to put earthquakes on these individual active faults and ignore the elephant in the room, which we're quite certain is a very large fault at great depth underneath the entire Tursky Range. Again, this is how in a tri-shear model you would make all those uphill facing faults. Again, we aren't completely sure. Again, it's possible that there is a fault that sort of curves where the bottom red dashed line goes and daylight's under the lake there. That's another possibility. But either possibility simply requires that these faults that we see at the surface are probably a secondary effect of something much deeper. And so when we're making our hazard model here, we probably need to put a very large source underneath the Tursky Range. And sorry, I forgot the little cartoon part. Thank you for the pictures, Reed, of how the tri-shear model will generate these faults that we see at the surface. Like I said, Reed continues to work in this area. Recently, he and Yasha, some of you may know, worked in Jumgal Basin, a place that Rob Langridge and Kanat and I worked light years ago as well. And they've done an excellent job mapping the structures here and profiling the terraces. And what they've done is characterize the ramp that's causing the Jumgal anticline there. And again, I think that the scale that Reed is working, I think is really the scale that we need to be working on some of these features. Of course, we still have to dig the trenches across the surface ruptures, and we still need to do all of those things. But we also need to start thinking about how what we see at the surface tells us about what's at depth. Once again, just to show some pictures, the terraces in the Tian Shan are incredible. Just a couple of pictures. The bottom one is where Steve Thompson worked. This is the fold, Achap Hills in Kashkor Valley. Far to the left is where the bedrock is over the neogene, but you can see the beautiful terraces and the involved neogene as you go to the right. To the left is a place that I like as well. Again, you see the folded neogene and the uplifted terraces. Really, by combining these, we have an opportunity to get slip rates on faults, but also to get at the subsurface geometry if we take the time to do the mapping and to profile the terraces. I want to show one more place, and then I'll stop and let people have some time. In Kashkor Valley, again, this is a place that we've worked quite a lot. We've taken some training courses there as well. Again, to focus on this theme on sort of the slip rate studies is the need to make good maps and to make balanced cross sections. This is a work of Katie Paulson, who did her master's thesis in this area. The map in the upper right is her map. Again, we start with the excellent existing maps and then we refine them. So really, it's quite easy to make, cover large areas because things are quite well known. We particularly picked this area. If you look at the bottom right, which is a balanced cross section she made, because we have the sediments depositionally on the bedrock on the left side. And if you look at the map, you can see that we can see this on the map as well. And then we can measure the thickness of the sediments that are exposed vertically, and then we can make a balanced cross section that allows us to figure out exactly how much displacement has occurred and the geometry, likely geometry of the faults. Other person I want to talk about is Wynne McLaughlin. She has worked mainly on the stratigraphy and paleontology of these units as well. And I throw this out for several reasons. One reason is to say, even the paleontology tells us something useful for seismic hazards. And also, I have a secret agenda here, which is that we've been collecting these amazing fossils in Kyrgyzstan, myself, for more than 25 years now. When I visit people, like when I visited Moscow University, other geologists who have worked in Kyrgyzstan showed me their collections as well. There's an incredible set of fossils. I would dearly love at some point for someone to throw a lot of money at me so I could build a facility that would allow us to properly archive and document and show all of the incredible fossils that exist in Kyrgyzstan and bring them back from places like Eugene and Moscow and others where they really shouldn't be. They should be in Bishkek. Briefly, what Wynne has done is by identifying the fossils and looking at their overlapping age ranges, she can, generally place the sediments to within sort of 4 or 5 million years based on overlapping fossils, depending upon exactly what we're lucky enough to have found. And then she does paleomag, which is something that Kanat and I also started way back in the Dark Ages. And she's been, at least in Kashgar Basin, able to nail down the boundary between the Sharpeldak and the Chu, which not surprisingly is essentially when the climate changed at the Pleistocene boundary around 2.5 million years ago. She's also nailed down the boundary between the Chu and Shamsi at around 7 million years ago. And we don't have a very good record in the Shamsi, but sort of extrapolating down, we think that what Kanat and I and others published way back in 2000, that the onset of the Neogene sediments is around 13 is correct, associated with the climate change. At the beginning, and that, the 7 million year old Chu Shamsi boundary and the Sharpeldak Chu boundary are indeed climate. We're talking tectonics here. Katie has made 3 cross sections through the entire set of structures in here. You're looking at them. A big unknown is the dip of the basement underneath it. The bottom 2 are the same slope we see on the backside of the Kyrgyz range, which is what we think is happening, but we don't know that for sure. We've made some with a flat contact as well, just to know that. And essentially, there's somewhere between about 5 and 6 kilometers of shortening since the Shamsi, the Chu Sharpeldak contact. Without going into a lot of details, the Sharpeldak and Chu are conformable in all the places we've mapped them. They actually interfinger quite a bit. You can see some lighter color things up in the Sharpeldak and darker things down into the Chu. And so we have essentially 6 kilometers of shortening in the past 2 million years. And we believe this is when the fault zone between the Tursky Range and Issaquah Basin extended into this area. It yields a slip rate of about 3 millimeters a year, similar to the late Pleistocene rate that Steve and others developed 20 years ago. And again, if you look at this figure to the right, which is something Kanat and I and others made in our 2000 work as well, which shows the elevation of bedrock. Everywhere where it's sort of smooth and stair-steppy, it's buried by sediments, so that's underground there. You can see the Kashgar Basin is not deep like the Issaquah Basin, and in fact, we think that the Tursky Range fault is growing into this area and integrating these structures as well. Again, something I haven't talked about, which these sorts of studies will also yield for us, is basin effects. For the National Seismic Hazard Map of the US, we've started to introduce basin effects too. given this erosion surface and our knowledge of actually the geometry and the depth of the basins in this part of the world, we could consider doing that in our seismic hazard maps as well. Okay, so I've probably gone way too long. I want to emphasize one last thing, and I have to show a picture of the bus, which is what transported us around through most of these studies, and make the point that, again, our current project, we are going to do the work as the process of teaching a combination of American and Kyrgyz students, and we'd love to have people from other groups join us if they're interested to learn how to do seismic hazard mapping. And we'll do this in the context of the class, the way we did our field classes in the past, which allowed us to do a lot of the work that I just showed you. And so again, as Richard pointed out, which is central to his grant and central to what we're trying to do, educating people is extremely important because, as I showed you, they're going to go on and do the work. Thank you very much. Now what?
Thank you.
I'm going to stop sharing.
Thank you. Thank you very
Anyone
much.
still awake?
All right, we are more than 100 people in this session, so I suggest if anyone has a question, just types a question mark in the chat window or even writes a full question in the chat window, please.
And Christoph, I assume you'll read them and I'll answer them.
Yeah, or perhaps if people just type a question mark, they can also tune in and ask them in person. Yeah, Valerio Poggi, please. What do you want to?
Yes, can you hear me?
Yes, I can hear you.
First of all, thank you very much for a very interesting presentation. This is, I think it's due. I have a comment and perhaps a question also regarding the initial part where you were mentioning why basically you have this kind of unexpected results of the previous hazard models, and you explained that the use of line sources is not appropriate. Somehow this is nowadays well known, and that's why, for example, in software like in OpenQuake, it is widely used the implementation of complex source models in where you have actually the full geometry of the fault, which is anyway difficult to constrain. So I fully agree on that point. However, I see that difficulties here is afterwards. So once you implemented the proper geometry of your fault, how do you compute properly also the corresponding ground motion, since most of the ground motion prediction equations are not capable to reproduce such a complexity, especially where it matters, so in the near field?
Yes, I agree with what you're saying. It is quite complicated to implement that. The simplest thing, which is a sort of thing that people have done with normal faults, is to simply take the distance from the site that you're interested in to the different places on the fault. And so that's sort of the simplest approach without going into detail. But you are completely correct. If you have a complicated shape and a shape that that you can't easily sort of say, here's where measure a simple distance to what you think is where the source of the energy is going to be, it is complicated. The thing you can also do, which is what essentially John Anderson did in that thing I showed, again, is to just assume a variety of sources at different distances consistent with the geometry of the fault and then assemble them. But I agree, it is a problem. And some people make discrete models where they actually, model the rupture on the fault using the geometry, but that's certainly beyond my capability and beyond what we're going to do in this class.
Thank you.
Thanks. There's a question from Tim Dawson. Are there any lessons from the Kyrgyzstan Merc that inform how we should be constructing seismic hazard models in the US?
Well, yes, I think so. I guess the theme that I'm trying to push, and I meant to say some additional words about the GPS and the seismology as well, is that we tend to work on these problems in narrow disciplines. So my experience working in the US is that generally the people making the models are seismologists or hazard people that don't understand geology, and most of us geologists don't understand seismology or geodesy. And so I think that the lesson I would say, and the sort of theme that I'm trying to push here, is that we need to be a little broader and we need to interact more. We can't be quite so siloed. I personally feel like I've learned an awful lot by having spent a lot of time interacting with my seismology colleagues and my geodesy colleagues. And I think in California, for example, the USURF process that I participated in was much more interactive in the sense that, you know, I worked with Tom Parsons' group on the geodesy model, and we went back and forth between the geodetic model and the geologic model. And I think just as a general lesson, I think that we need to interact more with people in these different fields that contribute, including even paleontologists. I see Wynn there. They have something to offer too. And so that's sort of the theme I'm singing today, is to be more interactive and to think not only about what your little piece of the puzzle is, but how it fits in. Now, other than that, you know, the geologic setting and the tectonic setting in the United States is, of course, very different than Kyrgyzstan. You know, we have a subduction zone off our coast, which is quite different than thrust faults in the interior. We have largely strike slip faults in California, and we have normal faults in the basin and range. So the lessons that we're learning from thrust faults in Kyrgyzstan, I think, will be more useful in other places that, you know, like Taiwan or parts of China or other places where we have stacks of thrust faults. Perhaps in the Alaska range, it would be useful as well. But for most of the United States, the tectonic setting is really quite different. But I do think we can learn in the sense of working more together and taking the time and effort to learn more about what the other fields contribute and how we might interact with them.
Thank you. Are there more questions?
Wow, I see a lot of students, ex-students on here. I want to take a moment to say hi and thanks to all of you, especially those who got up at outrageous periods of time.
Or then I might ask a question if you allow, Ray.
Of course.
So you said for Bishkek that probably there's not that much shaking to be expected because it's not sitting on the hanging wall of the thrust fault. And then you showed the cross sections by your student Paulsen, which showed actually thin-skinned tectonics, and we also saw that faults may extend at shallow depth way into the basin, and they may reach kilometers away from the mountain front. And what's also been shown in recent years, in recent studies, is that the earthquake recurrence intervals on individual thrust faults may exceed thousands of years or even tens of thousands of years. So I'm thinking, if there is such thin-skinned tectonics going on beneath Bishkek and a big fault coming from the south going all through the basin, and we just don't see it because it hasn't ruptured the surface in the past, say, 10,000 years or so, wouldn't then Bishkek not be in a very dangerous position and we should expect much higher hazard? And wouldn't it then be kind of a bit difficult or dangerous to say that there's less shaking to be expected based on the maps that we have?
Yeah, so let me first start by saying what we mean by less. The other thing Steve Thompson noted when I asked him about this, and maybe I shouldn't say it and so brought a company here, is that no matter which hazard estimate you look at, Bishkek is screwed. So when we talk about less, we're talking about, you know, maybe 0.6 G instead of 1 G in terms of peak acceleration. So again, it's sort of a, you know, it's either bad or really bad are our choices here. So don't get too carried away. We can't put the earthquake too far away. And I have an additional slide if you want to see it, that looks at estimates of loss of life and building loss, et cetera, et cetera. It's beyond my summary slide, but it's bad no matter which scenario happens, okay? The other point I want to make is that the Issaquah fault is the thin flap that is coming out into the basin. So if there's another one that's lower and deeper, we don't know about it, and there's certainly no geologic evidence of that. So the edge of the flap is the Issaquah fault, which is obviously at the margin of the city there, okay? So my point was more to address what the people at the embassy, because they were literally telling people to move out of their buildings on the southern margin of town and move to the northern margin of town until they saw the more recent results that were focused on the site response, which showed the northern margin of town was bad. So I suspect that it's going to be somewhat a wash when we're done, but we haven't done it yet, which is that there will be some sort of a gradient across the populated area due to the fact that the earthquake is largely generating energy to the south of town, but the site response will be greater to the north. And probably the result of that will be that the hazard will be reasonably uniform across the whole city. And that reasonably uniform value across the whole city will be bad, but not as bad as some of the publications suggest.
Thank you. More questions? Oh, this doesn't seem to be the case.
It looks like Alexander's talking into something.
Alexander?
I think he's muted.
We can't hear you, Alexander. Your microphone's not working. Alexander, can you just type the question into the chat room, chat window? If you're talking to us.
Maybe he's multitasking. I have to say hi, Kanat. It's so nice to see your face. And read. Well, I'm ready to go back to bed if everyone else is finished.
Okay. Alexander just said that
okay.
he's going to use another computer in a few minutes. So,
okay.
So we need more questions then.
Ray, I guess I had one question on the Issaquah work you were showing that you did with Reed, and you were talking about whether this is maybe a big all of the faults that you see on the southern shore of Issaquah are all part of this big kind of tri-shear arrangement. Is it possible also that if it may be some part of looking along strike, that because I think as you go to the east, things seem to all dip to the south. You go to the west, things are a lot more mixed up, and whether this is somehow a transition zone between those two different vergences. Is it possible that other models may also apply there as well?
Yes, and maybe Reed could chime in if he wants, but what's always struck me is that boundary, you know, the southwestern part of the Issaquah margin is really quite different again. That central part that I showed near Akhtarek has all those uphill facing faults. And then to the east, as you've noted, it's much more sort of a folding, and you don't see these structures, you know, going uphill. So I would say that there are probably 3 distinct segments that are somehow behaving differently. I suspect that at depth, there probably is some sort of a single large structure, but how they're deforming the shallower part is different. And in particular, if you remember that figure or look at the bathymetry, there's a very sharp edge in that middle portion on the floor of Lake Issaquah, which is suggestive that something daylights there, whereas you don't see any evidence of something daylighting on the southwest part or the southeast part. So I do think it varies in how it's manifested, just as the fault under the Kyrgyz range does as well. As you saw where we made that section, you know, 20 some years ago, on sort of the west side of the Chu River there, it's very different than what's happening at Bishkek, which is why one of the tasks for this project I'm working on is to make some good cross sections in the vicinity of Bishkek, including using the increased accuracy and number of earthquakes there. That one figure that I showed you that Steve Thompson and I made, supposedly, you can see that the faults were trying to follow earthquakes as well. So I think that there's seismological inferences. The other thing, again, to talk about the broader picture, I've shown a few people the geodesy, and we've tried to see if there's anything in the north-south profile in the GPS that gives us some sense of the geometry and the location at depth of the fault under the Kyrgyz range. And so Kai Johnson looked at this briefly for me, and there is some evidence in the curvature of the geodesy as you approach both the Issaquah fault and also the range bounding fault of the Tursky range. Somebody actually published a paper on this and argued that that curvature in the geodesy could be fault creep or something like that. But again, there's some possibility that the geodesy is good enough that we could sort of locate where the locus of strain accumulation is as well. So that would be another piece. So the goal in the cross-section near Bishkek is not only to look at the hazard maps and try to take what's good and bad from them, but also to make a good cross-section that uses the geology, the seismology, and the geodesy as well.
There's another question from Gordon, and he's asking whether precariously balanced rocks have been applied to constrain shaking levels.
I saw that note flash by, Gordon. And by the way, hi, Gordon. Not to my awareness, but maybe Richard or someone else or Kanat or someone would know. My experience is that there aren't a lot of obvious, I don't remember seeing a lot of really obvious precarious rocks. You saw that there's been some huge recent earthquakes. I think most of them have fallen down, but that might be something that would be useful. I'm not aware of anyone doing it. Looks like Richard has something to say.
Not about rocks, but actually one thing that, and Alexander, I'm sure, and Kanatbek agree with me on this one as well, that the record of landslides, large landslides, could actually have a lot to say from this if we could date them accurately.
I'm glad you noted that, because that is another thing I think is tremendously important. And that's why I showed that early figure. Those yellow splotches in the Issaquah map are landslides triggered by the earthquakes. I meant to say that when that slide went by. So if this was recorded, take a look at that when you go back. I agree. There are landslides everywhere. Careful mapping will reveal them. And I think a landslide chronology would be tremendously useful, but I'm just not aware of anyone working on that. We've got good Cosmo dates on boulders, on moraines, and on terraces. So I suspect, you know, we just published a paper in the San Bernardino Valley where we used cosmogenic dating on blocks of landslides to get a slip rate on the San Andreas. And so I think the combination of cosmogenic dating and landslides could be an extremely valuable approach in Kyrgyzstan.
May I have a comment? Do
Yes.
you hear me now?
Yes, we hear you.
Yes.
And see you.
Generally, there are few studies. Oliver Korov dated few. We dated few within the summer school, but they are very, very limited. It is just at the beginning, because the main methods that can be used actually are cosmogenic and OSL. And both are, I would say, expensive. We face some problems on it. For example, with Korean guys, we dated one rock avalanche about 2 billion cubic meters in volume, not far from Karakul. And we got one age. We sampled quartz veins from a very limited area. And one age gave us 70,000, one sample 50,000, and three sample 40,000. And I must say that we stopped on 40, but actually, when I looked on it just as a geomorphologist, I would say that it is younger. So it is. We must be very careful, because ages, they have a lot of constraints. And what I also want to say, if our boss will allow me to use a few minutes, you see, thank you first of all for your very interesting presentation. But what I could see that models of how these faults propagate down deep, at the moment there are models. We do not have real, say, direct geophysical data. Of course, we do not have borehole data. That is why I think might be very important to focus on some sites where we can get some additional information, maybe not from these profiles as you demonstrated, that can shed some more light on the propagation of rupture surface in the Earth's interiors. And I want to show, if I can share my screen, I want to show you one site. I will try. No, I cannot. Chris.
You're a co-host now. Now you can share, Alexander.
Так.
Hold it up.
I will. Okay. Do you see my screen?
Yes.
Yes.
Here it is Google Earth. It is upstream from Taktagul Reservoir, in the very, I would say, remote area where the Kambarata Reservoir should be built. And here you can see this caldera-like feature. It is very strange phenomena where about 3 cubic kilometers of rock disappeared in ridge interior. It is not a landslide because there was no free space where to slide down. I will show you, I will try to show you, just a moment. Yes, it is how it looks on the older space image. You can see rhomboid shape feature, and you can see altitudes all around and in. And the mean depth of this hollow is about 500 meters. And I want to show you, just a moment. Yeah, how it looks like, how it looks. You see that it is very young because it disrupts modern, recent topography. How it looks in the cross section, you can see. And actually it is the model, how it could be formed. That the idea was that it could be a recent fold with a hollow, say, tectonic cave in it where this amount collapsed. It's my crazy idea because I could not find any other explanation to find the place where recently 3 cubic kilometers of rock could disappear. But if it is more or less correct, then it can give some additional inputs to think how this neotectonic folding could develop. And I think it might be very interesting, especially from neotectonic viewpoint.
Thanks, Alexander. I think there's only one way to find out. We have all to go to the field after Corona is over and have a look at ourselves.
Yeah.
Yes, this site is now on my list.
Okay. on my too. I was there actually once, 41 years ago.
I would like to say one more thing about the balanced cross sections. Obviously, we can draw a variety of cross sections, but if they're balanced, at least they can be correct. The other piece that we've ignored, in my opinion, is the excellent Soviet era maps, because the bedrock geology is quite well known. The fabric, the dip, the geometries in the bedrock structures have been mapped and are well known. And in fact, Craig Tozer, who was another student who worked there, looking at the reactivation of faults, found that the bedrock control is very important. So that's another clue that we have. In some areas where the bedrock is well exposed and there's a fabric or geometries, those could be helpful in terms of limiting the number of choices that we have in terms of how to balance the cross sections. However, having spent time making balanced cross sections, it's pretty challenging to make some that actually work. You think it's easier when you look at something someone's published, but you actually try to do it, you find out that what you think is happening isn't actually working until you try a whole bunch of different things. So while it is a model, it is at least a self-consistent model. And if we can get some additional constraints like the location of earthquakes or the likely geometry or location of the fault at depth geodetically, or use the gross fabric or shape of the bedrock structures, I think we can make pretty good cross sections. Now, I'm not saying that all of you guys, digging trenches and doing slip rate studies and mapping landslides should start making balanced cross sections. My point is that there's a lot of input from other areas that we haven't been integrating. And so really the song I'm trying to sing here is we need to integrate more. We need to talk to our colleagues. We need to say, what additional information do we need? Does it exist? Can we get it? And how do we integrate it? That's really the integrative piece. And that's why I was so excited about what Richard is doing here, because if there's, I think he said there was up to 100 people listening at some point, we're going to have a wide variety of expertises that are thinking about this problem, and this broader integration and synthesis that I think is necessary could be done. And I focused on the cross section and where the fault is at depth as an example. I'm not trying to say that's the only thing we should be doing, but I wanted to highlight it as an important thing that we're not doing. And there are other important things we're not doing as well. And I want to encourage everyone to think creatively about what they are and what they might add. I would also make the point, some of you know this, probably many of you, Kanat Beck's PhD thesis was on the terraces, right, Kanat? And that's how I got excited about the terraces. When I first went there, when was it, 94, a long time ago? Because Kanat kept pointing out the terraces and talking about the terraces. And, you know, I had never worked with, you know, things like this much. And I still think there's a tremendous potential in the terraces, in the geomorphic landscape that Kanat introduced to me so long ago. And again, that's just one area. We need to be thinking in a more synthetic way so that we can put whatever information we have into these hazard estimates. And again, Steve, I'm sure is going to still tell me that the uncertainties of all of these models are going to overlap, but at least we'll be able to say where in the uncertainty we think things are.
Wonderful. Thanks a lot, Ray. So there don't seem to be any more questions. Is that right?
I need more coffee.
I believe that.
Thank you very much, Ray. Thank you to everyone who's been here and listened, especially those who have got up early and stayed up late. And look forward to seeing you all again at the next one of these. Thank you.
Okay, thank you.
Goodbye.
And thanks so many of my students. So nice to see so many of you.